Okay, so we're doing the finding prime numbers task. This is the last programming task of logic exercise, part of week 1, dealing with data. So if you go onto the tab here and open your repo, you should get this window here. You have preloaded code and problem statement. So the task that you're expected to complete is find given a number a, determine whether it's prime or not. And the way you formulate that accurately is given here. So your code should return 1 if a is prime and 0 otherwise. Okay, and you should do it using these two definitions. The first is the formal definition of a prime number, which you should be familiar with this from other modules, and it says that a natural number p is said to be prime if it is greater than 1 and if its only divisors are 1 and p itself. The other definition is for any number that is not prime, there exists a number a which is greater than 1 and less than p, which divides p. Okay, so using these two definitions, we can now start writing our function. And it's helpful to consider that in mathematics there is no formula to find all prime numbers. The closest thing we have is an exclusion of non-primes. So given a set of numbers, you take out the numbers that have divisors other than 1 and the number itself. So as far as we are concerned, any number is prime, and that we formulate with this statement here. Any number a is prime unless the following condition holds. So using this definition here, for any number that is not prime, there exists a number which is greater than 1 and less than p, which divides p. Okay, so if such a number exists, then the number that we started with, p, is not a prime. And we express that as such. We say if, so we loop over the numbers that are between 1 and p. So for I in range 2, which is the first number greater than 1, and a, which is the number that we want to determine whether it's prime or not. Okay. One thing to know is that as I changes from 2 to 3 and all the way up to a, it is important to note that it is not inclusive of a. So it will never be a. The maximum value of I in this loop will be a minus 1, which is exactly what we want it to be, given that the definition holds for numbers that are greater than 1 and less than p. So in this range here, we want to determine if the number, if this number here divides a. And the way we do that is using the modulo operator to determine if it has a remainder of 0 after division by some number. So if a modulo I, if a is divisible by I, or in other words, I divides a, then a modulo I should be 0. And if this condition holds, then a is divisible by I. And if a, which we suspect is a non-prime, then in this case its prime number status is 0, because it is divisible by a number that is between 2 and a itself. So now if this condition holds, then A is no longer a prime as far as we're concerned. And if this condition is not true, then we resort to the initial value of is prime, or the prime status of A, which is that it is a prime, or its is prime property is equal to 1. In any case, after this, after we've checked whether it's prime or not, we need to return the is prime property from the function. And it's also good to know that in this loop here, it will loop from the first prime number, which is 2, all the way to 100 inclusive. As I've said before, in Python, the upper bound is the upper bound in a 4i range loop. The upper bound is the second argument, which is 101 here, minus 1. So the maximum value will be 100. And every time this loop executes, it will check if the function is prime given an argument A, tells you that the number A is prime. And if it does, then it prints that number. And that's essentially what this loop does. So if you run it, it will give you all the primes from 2 up to 97, which is the last prime before 100. Now you run your tests to see if it passes, and it does. Submit, run the tests one final time, and it checks out. So